Okay, so I think we're back. I'll wait for a couple more people to get in. So basically this video, I'll wait for more people to get in, but it's going to be about Apple's thermal design, if you could call it that. Just waiting on a few more people to get in here. And I'm going to show you what I did to this MacBook to keep it, no sound? Should be sound. Sounds echoey. Hang on a second here. Yeah, I see why. Hang on. Alright, is that better? That should be better. Yeah, there's two mics enabled. They're the same mic enabled on, okay, so this is a MacBook Pro 15-inch that had a dead GPU. I did the EFI modification to it, and it works good now. However, when rendering a 4K video, and this is with good thermal paste, this has nothing to do with my thermal paste, it gets to about 97 Celsius. That is 3 degrees from T-junction max, which is the maximum temperature that it'll allow on the die. So Apple will, the way they have the fan profile set up on these things, it will wait until it gets to 90 degrees Celsius before increasing the fan speed. That is absolutely ridiculous. It should be kicking on the fans well before 90 Celsius. And it goes off of package temperature for fan speed. So package temperature is probably going to be 3 to 4 degrees cooler than the CPU core temperature. So, but when Intel recommends that the full cooling capacity is reached at 90 Celsius, so that means fan speeds are on max at 90 Celsius for core temp. So the way Apple has it set up, package temperature and it reaches 90 package temperature and it reaches 90 Celsius will trigger the fans to go to max, but core temperature may already be 93, 94 degrees, and that's not following Intel's design recommendation for, you know, long-term life, even though Intel does not die. So let's go over Intel's and just a quick thing to show you guys on my own thermal design. Check this out. It has plates now. So so let me pull up a data sheet for this CPU, and I'm going to close this window down a little bit. Really small. Oh, actually, you know what? I'm going to leave it here, and I'm just going to shut that off for now. And we are going to look at, we're going to go to Intel. This is a 2720 QM. So this is a quad-core, 8-threaded CPU. And this is an i7. These things run hot as they are, but with my custom fan profile, this thing won't go over 80 now. Barely over 80. Right now running the streams at 81. And that's perfectly acceptable for an i7. That's cool for an i7. So let's look at Intel's design recommendation. Let's see, where is it here? Data sheet. Right here. Intel redid their website a while back. I like their old website better. So this is a second generation mobile. Be in volume 1. Seriously? Really, Intel? Okay, let's see if I have it downloaded. I may have downloaded it. That's stupid. Did you put taller feet on the bottom? Yes, I did. So let me show you guys. And now we gotta figure out what to talk about now because Intel decided to remove their... So, the bottom, I cut 2 holes and I put these plates. It looks pretty decent. Works excellent. If it doesn't shut off, it's not running too hot. Manufacturers, exactly. So let me see. I may have saved this Intel datasheet. If not, I have no idea why they would. Let me see here. Right here, select second generation cores. Okay. Okay. So let's look at thermal. Let me find it here. Should be here. Thermal management and thermal considerations. We're going to start here. So the thermal solution provides both component level and system level thermal management to allow for the optimal operation and long-term reliability of the Intel processor-based systems. The system processor's thermal solution should be designed so the processor remains below the maximum junction temperature TJ max specification at the maximum design power TDP. Conforms to system constraints such as system acoustics. We don't care about that. System skin temperatures. I don't care about that either. And exhaust temperature requirements. I don't care about this either. I could care less about having my fan speed on low just so the exhaust temperature is cooler. That makes no sense. You know, yeah, if it's gonna burn someone, fine, but continue on. Thermal design power and junction temperature TJ. So the processor TDP is the maximum sustained power that should be used to design of the thermal solution. TDP represents expected maximum sustained power from realistic applications. TDP may be exceeded for short periods of time or if running a power virus workload. Due to Intel Turbo Boost technology, applications are expected to run closer to TDP more often as the processor attempts to take advantage of available headroom in the platform to maximize performance. Now here's the thing. According to Intel and according to this was still turbo boosting at 97 Celsius. That is pretty hot. So what is their thermal headroom? As long as it's below 100, it's okay? That makes no sense. See, right now with my cooling profile, it's staying below 80, and that is just perfect. Processor may exceed thermal design power for short periods of time after a period of lower power operation due to its turbo feature. This feature is intended to take advantage of available thermal capacitance in the thermal solution for momentary high power operation. The duration and time of such operation can be limited by power runtime configurable registers within the processor. I have no idea what that means. The processor integrates multiple processor and graphics cores on a single die. This may result in differences in power distribution across the die and must be considered when designing the thermal solutions. Thermal considerations. Intel Turbo Boost technology allows processor cores and processor graphics cores to run faster than baseline frequency. During a turbo event, processor can exceed its TDP power for short periods. turbo is invoked opportunistically and automatically as long as the processor is conforming to its temperature, power delivery, and current specification limits. So what this means is Intel does not care how hot the processor is running as long as it's running below TJ max. If you hit TJ max, it will not shut off right away. It will throttle first. So when you hit TJ max, it'll start throttling, and it's still not going to shut off probably until it gets to 110, 120. Who knows? Yeah, that's what I did. I put four feet and these things at the bottom. I'll show you. So it has, you know, holes now that it can actually breathe. So let's go back to where was I? Thus, thermal solutions and platform cooling that are designed to be less than thermal design guidance may experience thermal and performance issues, since more applications will tend to run at or near the maximum power limit for significant periods of time. Okay, we don't really care about turbo boost. This isn't relevant. We don't care about this either. Thermal and power specifications. Here we go. So let me scroll through. And figure out let's see. Okay, thermal management features. Processor package thermal features. This section covers thermal management features for the entire processor complex, including the processor core, graphics core, integrated memory controller hub, and will be referred to as a processor package or simply the package. Occasionally, the package will operate in conditions that exceed its maximum allowable operating temperature. This can be due to internal overheating or due to overheating in the entire system. To protect itself and the system from thermal failure, the package is capable of reducing its power consumption and is therefore its temperature to attempt to remain within normal operating limits using the adaptive thermal monitor. So let's talk about something right now. When this CPU was rendering a 4K video in this, it was hitting 97 Celsius and throttling. Or wasn't throttling it. So if rendering a 4K video is making it throttle, okay, think about, so that's going to start throttling and that's going to bring it back performance-wise. So think about now that it's running cooler and it'll run about 80 when rendering a 4K video. You can get more performance out of that CPU. You would get a little more power out of that CPU since now it has more thermal headroom. It'll be able to stay in its turbo boost bracket for a little bit longer now that it's cooler. So when Apple designed this computer, has no bottom ventilation whatsoever. The fans don't even barely run until it gets to 90 Celsius. Heatsink design it's okay. It's not the best. It's not bad. But it has no bottom ventilation. Try getting an i7 to run cooler than 80 under load. You will not. They can get so much more performance out of that chip if it ran cooler, because it's going to hit its point where it's going to throttle it back, it's going to reduce its power consumption, and performance is going to drop. So let's continue on. So this will be able to handle, now that the holes have been cut on the bottom, it'll be able to handle a little bit more than, you know, if it wasn't. So let's continue on. The adaptive thermal monitor can be activated when any package temperature monitored by a digital thermal sensor meets or exceeds maximum junction temperature TJ max and asserts processor hot. Thermal control circuit TCC can be activated prior to TJ max, but the use of the TCC activation offset. The assertion of processor hot activates the thermal control circuit and causes both the processor core and graphics core to reduce frequency and voltage adaptively. The TCC will remain active as long as any package temperature exceeds the specified limit. Therefore, the adaptive thermal monitor will continue to reduce package frequency until voltage and TCC is deactivated. Adaptive thermal monitor protection is always enabled. So what PB Henry was saying with Razors is the NVIDIA chips. Razer has them set to throttle at, you know, to 15 to 10 degrees Celsius above their TJ Maxx temperature. See, Intel does not allow you to do that, so that's a good thing. Yeah, I made this MacBook better. It was dead when I got it, and I disabled the graphics chip. So, adaptive thermal monitor. The purpose of the adaptive thermal monitor is to reduce processor core consumption and temperature until it operates at or below its maximum operating temperature, according to TCC activation offset. Processor core power reduction is achieved by adjusting the operating frequency using the core ratio multiplier and input voltage, modulating starting and stopping the internal processor core clock's duty cycle. So how this would do it, I don't know. If it would do it by the external clock chip, I'm not sure. Temperature at which adaptive thermal monitor activates the thermal control circuit is factory calibrated and not user configurable. The default value is software visible and the temperature target, whatever. The adaptive thermal monitor does not require any additional hardware, software drivers, or interrupt handling routines. The adaptive thermal monitor is not intended as a mechanism to maintain processor TDP. This is where Apple gets wrong. They rely on this. It will throttle. The system design should provide a thermal solution that can maintain TDP within its intended usage range. So, let's think about something. When you have a high-powered graphics chip running at full load, and your high-powered quad-core CPU running at full load, all that heat in the heatsink. Think about just the CPU is getting up to 97 Celsius. You're going to tell me that with two chips pumping heat into that same heatsink that it is not going to throttle? It will throttle. And that's where they get wrong. I really don't think that this would meet what Intel is suggesting here, because it will rely on throttling on either the CPU or the graphics chip to maintain that temperature bracket and maintain that power consumption. So, upon TCC activation, the processor core attempts to dramatically reduce processor core power by lowering frequency and or voltage operating point. The operating points are automatically calculated based on the processor core itself and do not require the BIOS to program them as with previous generations of Intel processors. Oh, wait a second, this is wrong. I should have this shut off so you guys can see what I see. Sorry about that. So now we should be able to see what I was reading. I apologize for that. I had that open the whole time. So, let's continue on. Operating points are automatically calculated by the processor core itself and do not require the BIOS to program them as with previous generations of Intel processors. The processor core will scale the operating points so that the voltage will be optimized according to temperature, core bus ratio, and number of cores in deep sea states. Core power and temperature are reduced while minimizing performance degradation, whatever. A small amount of hysteresis has been included to prevent an excessive amount of operating point. This doesn't matter. Neither does this. Let's see. So this is sort of important, but I'm not going to read it. It doesn't really matter that much. Each processor execution core is an on-die thermal sensor that detects core's instantaneous temperature. The DTS is the preferred method of monitoring processor die because it is located near the hottest portions of the die, and it can accurately track die temperature and ensure the adaptive thermal monitor is not excessively activated. Temperature values from DTS can be retrieved through software, whatever. I don't care how it's retrieved. So here's where another thing. I'm not 100% sure, but I'm pretty sure what Apple goes off of is package temperature, which is this right here. and that would be the sensor located on the CPU. Not on the core, but it's going to be like a variable resistor on the substrate of the CPU itself. Not 100% sure, but that's what I think. So that's going to be a little bit that's going to be a little bit cooler than the cores itself. So, like, let's look at our core temp right here. We have core 1 72, core 2 75. Okay, you guys get this. So CPU proximity is 62. CPU diode. This is what Apple, I think, is going to be using. Is going to be the CPU diode, and that is 71. And you see that is a few degrees cooler than the cores. So we're going to continue on in the document. I'm going to show you why that's going to matter. So just go to chat, see if there's anything important going on. The BIOS has nothing to do with it, but keep reading. No, I'm not talking about the BIOS. I'm just reading. So, digital thermal sensor accurate. Yeah, it's going to be a few degrees different. Processor hot signal. Processor hot is asserted when the processor core temperature has reached its maximum operating temperature, TJ max, for a timing diagram, whatever. I don't care about that. Only a single processor hot pin exists at a package level. When any core arrives at the TCC activation point, processor hot signal will be asserted. Processor hot assertion policies are independent of the adaptive thermal monitor enabling. I smell something burning. I don't know what that is. It's not this. This is really cool. I'm going to be right back. I'm going to go get some water. Give me about 30 seconds. So let's continue on. Bidirectional processor hot. By default, processor hot signal is defined as an output only. However, the signal may be configured as bidirectional. When configured as bidirectional signal, processor hot can be used for thermally protecting other platform components should they overheat as well when processor hot is driven by an external device. The package will immediately transition to the minimum operating points, voltage, and frequency supported by the processor and the graphics cores. This is contrary to the internally generated adaptive thermal monitor response. Make sure I have the right view. Yep. Clock modulation will not be activated. I'm not sure what that means. If it's signals asserted, I'm pretty sure it's going to be reducing the clock. TCC will remain active until the system deserts processor hot. This is actually controlled by the SMC. If you could look up on the schematic, you'll see it. The processor can be configured to generate an interrupt upon assertion and deassertion of the processor hot signal. Toggling processor hot, that doesn't matter. Voltage regulator protection. This doesn't matter much anyway. Thermal solution design and processor hot behavior. With a properly designed and characterized thermal solution, it is anticipated that processor hot will be asserted only for very short periods of time when running the most power-intensive applications. The processor performance impact due to these brief... Okay, here's one thing. This is nonsense. This should never be asserted. You should never get your chip this hot that you need to activate its thermal protection. My Lenovo, I could run that thing at maximum load, CPU, graphics, and turbo, and it's not even going to be close to that. This will throttle. So low power states, and processor hot behavior. If the processor enters a low power package idle state, C6, C7, whatever, I don't care about that. Thermal trip signal, regardless of enabling automatic or on-demand modes, in the event of a catastrophic cooling failure, it'll shut off, basically. This doesn't happen until really hot, like 110, 120. So critical temperature detection. Critical temperature detection is performed by monitoring the package temperature. Now, with this feature is intended for a graceful shutdown before the thermal trip is activated. However, the processor execution is not ensured between critical temperature and thermal trip. So here's what I figured out a while ago, is the CPUs are not shutting down basically to protect themselves from damage, because you have to get that die very, 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 very hot to damage it. Why it's mainly shutting down is to protect your data. The processor is doing so many things at once, and such a little, just calculating numbers just slightly wrong is going to screw up your data, and can screw up your data. So when it shuts down before this prevents it from happening. If you kept the chip going, you're going to be able to get pretty hot and still be able, the chip's not going to get hurt. Think about when we solder the chips on. We're getting them very, very, very hot. And for short periods, that's fine. Like, for example, example of this is if you blue screen when your CPU is hot. That would mean that, it executed something wrong and screwed up. This is why you shut down, to protect stuff like that from happening, and to protect your data from corruption. Yeah, mid 2010. Mid 2010 is dual core. This is a quad, and this I have exactly this. The Apple doesn't have engineers but hipsters. Exactly. Here's another stupid thing on this thing. There is no eject button for the CD drive. There's something that looks like it has an emergency pin, and you try sticking something in there, it doesn't do a thing. There's nothing there. Why they would do that, that's just stupid. Exactly, they designed it for style and not for usability. It's stupid. No, I could care less how it looks. I could care less if that has two big holes in the bottom. As long as it doesn't shut down, I don't care. So continuing on, see if there's anything else. Okay. Digital thermal sensor based fan speed control, T-fan, is recommended as a recommended feature to achieve optimal thermal performance at the T-fan temperature. Intel recommends full cooling capacity well before the DTS reaches TJ max. So let's go back again. The CPU diode, what Apple is using for fan control, is going to be a few degrees cooler than the CPU core. So by the time they increase the fan speed to full, the CPU will have already met, it would not meet this recommendation here. So just because the fans are full at diode does not mean the fans are full when the cores are, just because diode is at 90 doesn't mean the cores are not already at 94, 95, and this is giving you a lot less headroom. So like, let's look at our core temps right now. And that doesn't want to open for some reason. Or did it open? No, don't want to open. Why? Okay, whatever. But your diode temperature is going to be a few degrees cooler than the core temperature. So by the time it doesn't really meet this very well. So just because your diode is at 97 means your cores may already be 101, 102 in throttling. Again, that's not going to hurt the chip, but not good for it. But with a custom fan profile, it cools fine. If Apple would just put tiny vents on the bottom near their fans, it would not throttle like this. It's just stupid to have no bottom ventilation. Same thing with the fans. I don't care if it's a little loud. I could care less about that. Let it cool. You know. So that's pretty much it in the data sheet. Now, as an example, as this is watch your load temps, and what if it gets so hot that it blows the diode? It usually won't. Some stuff like AMD stuff a long time ago would blow the thermal diode, and it would just smoke. You just literally smoke, but that doesn't. OBS is frozen here, so I have no idea if I'm streaming or not. So is OBS working? It seems to have. I don't know what happened. Okay, so OBS seemed to have messed up. No idea why that would be, but so before I modified the vents on this thing was running at 90s streaming. It's low 80s, right? I keep opening the wrong thing. I want to open Intel. So it's at 84, 85, perfectly fine for an i7 running this workload right now. But my point is the thermal design on anything. Look at a MacBook Air. Okay, look at a MacBook Air board. Look at the size of the heatsink. I mean, it's stupid. Let me see, I have no way of knowing what I'm showing you, so I have to wait for the delay. But look at the size of the heatsink. It's tiny. It barely will be able to dissipate that heat from the CPU. It's just tiny. Compare that to a Lenovo or even a Dell. That the heat sinks on Apple stuff is just lousy. Even just increasing their fan profiles would help. But bottom ventilation, that's why I have no idea why. It makes no sense of why they don't include bottom ventilations on any of their stuff. You'd think that they'd lost enough money on the 2011s having to pay for new boards in them, that they would get the message that, to make bottom ventilations on their stuff, but they don't learn. Look at 2014's. NVIDIA chips are already starting to die. Just never ends with them. So, what is my battery temp? I have no idea. The program that shows me has not decided to work. Let's see if I go on this way. Here we go. Let me just make sure I didn't change anything. So I have it set up right now to start speeding up at 50 and go full at 75. So my battery temperature is 23, 23, and 31. So about 23. That's perfectly normal. The GPU diode, this is disabled. This is just heat from the CPU that's blastering it. Again, all these sensors is dumb too. You only need a few. So yeah, battery temp is about 23. Pretty normal. And my ambient is going to be probably fairly close to that. That's full charge, of course. If I unplug it, it'll go up a little bit offline. So am I still offline? I have no idea. Yeah, now I'm streaming. That's the internet, that's Time Warner. It's later, and that's what Time Warner does. So pretty much that's what I wanted to cover, is just Apple's thermal design is lousy, and you can improve it by cutting holes in the bottom of it. I switch it off and on again. No, I didn't do that. It just came back randomly. But on top of that, I think I'm done for the night. I just wanted to show you guys that the thermal design barely is going to meet. It probably won't even meet Intel's design recommendation, given the fact that the way the fans start increasing to full at 90 Celsius on package temp, but cores may already be higher than that. It just doesn't. And that's with no GPU load. With GPU load, there's no way that both of those chips are going to stay at their recommended temperatures. You know, it's just dumb. So on top of that, I think I'm going to end the stream. So thank you everyone for watching.